So let's get started. So it's our pleasure to welcome Professor Shinsei from University of Chicago visit us, give us this very honored lecture, 施慎谦lecture. So I would like to ask the Professor Yu, the chairman, to give us a small talk first.
Okay, small.
or a long talk.
I just want to say a few words. It will be very brief. First of all, I want to say it's our great honor that Professor Shinsei Yu, right, can come to National Tsinghua University and deliver this 慎谦师 lecture, which is a very important annual event in our department. Professor Yu is a well-known expert on the condensed matter theory of some quantum mechanics aspect. So I believe we can learn a lot from his talk today. And I'm also hoping during his visit, some of our colleagues and their student or postdoc can discuss with Professor Yu and maybe exchange ideas and explore some future collaboration. So in this case, I believe the talk, your talk, and your visit will be very fruitful. Okay. One more thing I want to say is Professor Zhi Gang Shi is not around, but I will say something about this 慎谦师 lecture, right? Professor Zhi Gang Shi, who is a professor in University of Texas Austin, he is an experimental condensed physicist, right? And he is an alumni of our department and donate money to support this lecture. Okay, and this is second year. So in memory of his father, so we are also, on behalf of the entire department, we are also very grateful for Professor Zhi Gang Shi. Okay, without further ado, I will give back to Bo Yang. Oh, yeah, sure. Oh, that's right.
So we have a memorial plate for you.
So we have a small souvenir plate,
for
commemorative plate for Professor Yu.
Yeah. Yes, so.
Yeah. Wow. Okay. Could you come to here?
Yeah, maybe we want to take a pictures. This is for.
Oh,
yeah.
Okay. Okay, great. Okay.
Well, thank you very much.
Yeah.
Oh, wow.
So that's the logo of our department. Department has the logo of National Tsinghua University.
Oh, wow.
Yes.
That's great.
Okay.
Thank you very much.
You want to give some introduction about Professor Yu?
Yes, so let me give some also brief introductions for Professor Shinsei Yu. So he graduated from University of Tokyo, get his master and the PhD degrees in applied physics, and then he did his postdoc in KITP and then in Berkeley, and then he moved to UIUC, and I'm fortunate to have Shinsei. I was fortunate to have Shinsei as my PhD advisor at that time, and then he also moved to U of Chicago right now, and then he is a world-class physicist working on multiple disciplines, including condensed matter theory, quantum information, high-energy physics. He's really famous on a conjecture called Liu-Takayanagi conjecture. Basically, this is also one of his topics today. And then it's about relate entanglement, quantum entanglement, and then with the geographic meaning. And then he's also famous on his classifications of topological basis of matter, which give a huge impact of nowadays people try to do this topological chemistry. Okay, he also won various prizes, including Nishina Memorial Award, and then he also elected the top 10 young brightest mind in the world in the Science News, and then also he's current Sloan Fellow and then the Simons Investigators. So I can speak like a half hour just discuss how good he is, very inspiring people. So I will stop right now. So I will give the microphone to Professor Shinsei to give his lecture.
Thank you very much. Thank you for the invitation. Thank you for the nice introduction. Yeah, so coming from Chicago, I was very surprised that this place is so warm. And I was also very surprised to see a lot of friends. And I'm very happy to get to know a lot of new people too. So today I want to talk about the kind of interplay between quantum entanglement and the geometry. I guess one key idea is that the concept of quantum entanglement is becoming so important in understanding the physics of many body quantum systems, such as condensed matter systems and the perhaps nuclear or other systems as well. Today I will first introduce this importance of quantum entanglement by taking some examples, mainly from condensed matter physics. But then later on, I will focus on the particular kind of quantum many-body systems, which I would call the holographic quantum systems. And these are particular quantum systems which admit some geometrical or gravitational descriptions. And then I will introduce our recent research on the understanding of quantum entanglement in holographic quantum systems. Okay, but before discussing, so this is my outline. But before discussing quantum many-body systems, we should really start from the simplest quantum systems, where we can discuss a quantum entanglement, so that this is the system discussed by Einstein, Podolsky, Rosen, EPR. So they just consider a system of two spins, 2 spin 1/2 degrees of freedom, and this is the minimal model to understand the bizarre nature of quantum correlation. So that's a quantum entanglement is a consequence of applying quantum mechanics to many-body quantum systems. So they consider particular linear superposition of this kind, spin up down minus spin down up. So we consider linear superposition. This state is somewhat bizarre because basically measuring one of the spin automatically determine. Oh, that's right. I should be using this because I'm holding this because I got confused. So so this state is bizarre in the sense that measuring the one spin automatically determine the spin state of other particle. Even if these two spins can be very far apart, like intergalactic distance. So this is the kind of minimal model of quantum entanglement, and Einstein called it a spooky action. Nowadays, people get used to the concept of quantum entanglement, and I think right now there's a lot of excitement or expectation to actually use a quantum entanglement to do something useful, such as quantum computation or quantum communications. So what is really happening here is that we are talking about quantum mechanics. So we are taking superposition of two states. So that's where this quantum strange quantum correlation comes from. So this state should be compared with the simpler state where we don't have any superposition, and in this case there's no quantum entanglement. This state is called product state because it's given by a single product, but this state does not have quantum entanglement. So it doesn't depend really on. So the state of the first spin doesn't really depend on the state of the second spin. They are just uncorrelated. To be more quantitative, we can discuss how we quantify the quantum correlation or quantum entanglement included in a given quantum state. So the idea is to use this partial trace, where basically we decide not to look at the second spin. Okay? If you compare these two states, if you take this simpler state, if you decide not to look at the second spin, because these are just a given product, it doesn't really affect the first spin. Whereas if you consider this more interesting entangled state, if you decide not to look at the second spin, basically you don't know what is happening to the first spin because of the correlation we talked about. So that means if you decide not to look at the second spin, you basically gain ignorance, or you can say there's entropy associated to this ignorance. So you can quantify the amount of quantum correlation by defining the entropy or ignorance if you decide not to look at the second spin. So this is a concept of entanglement entropy. Okay? So for the case of this EPR pair, the simplest entanglement state, this entanglement entropy is given by log 2. Basically, if you decide not to look at the second spin, you don't know if the first spin is pointing up or pointing down. So that's why you get the log 2. Whereas if you look at this first kind of state, this entropy associated to entanglement is just 0. So this is a way to quantify the quantum entanglement associated to a given quantum state. So this concept, quantum entanglement, has been around quite some time, but for me, a quantum condensed matter physicist, problem is much more complex than just an EPR pair. Okay, so typical Hamiltonian, which we have to deal with to understand condensed matter systems, maybe something like this. So the point is that there's so many particles, and they may be strongly interacting via some potential, maybe Coulomb interactions, something like that. And if you are perhaps nuclear physicist, you may be interested in systems described by this type of Lagrangian. It's like quantum let's say QCD Lagrangian. Okay. So these models are so strongly interacting, and in many cases we don't know really how to solve this. These type of strongly interacting systems may exhibit rich varieties of phenomena. For example, if you look at the ground state of this Hamiltonian, it may exhibit superconductivity, quantum magnetism, or something like topological phases of matter realized in the fractional quantum Hall effect, and so on and so forth. So as a condensed matter physicist, our task is to understand the possible phases of matter and the mechanism of these phases of matter. And we also want to find a way to diagnose different states of matter, which may happen, which may be realized in this quantum many-body Hamiltonian. Besides static properties, such as the ground state of these Hamiltonians, or maybe the structure of the phase diagram, and so on and so forth, we may be also interested in non-equilibrium or dynamical properties, and so on and so forth. So I'm talking about this type of Hamiltonian, which is called the Heisenberg model. So this is supposed to be, because this Hamiltonian is rather complicated. So let's just think about simpler Hamiltonian, where electrons don't move, but nevertheless they still interact by spin degrees of freedom. Okay, so then one could ask, what could be the ground state of this Hamiltonian? Okay. One possible ground state, maybe so. Yeah, this model is defined on some sort of lattice. Let's say something like a square lattice, and then the possible ground state can be visualized or picturized, something like this. So basically, it's some spins. They're pointing some direction. Let's say for A sublattice, it's maybe pointing up. Whereas for B sublattice, spins are pointing down. So this is another, it's an example of product state. This is called Nail state. Nail state. Okay, so this is the one possible ground state. And clearly this is another example of unentangled ground state. Okay, and somehow this unentangled state was too difficult to show on the screen, so it didn't show up. But this is an example of unentangled state. We could have slightly more complicated state where ground state may be looking like this. So once again, it's a square lattice. But now we may have EPR pairs, or condensed matter theory, people call it the dimers. So each oval represents spin singlet. And then this EPR pair basically covering the lattice. Okay, this is called valence bond solid state. This is another example. This is slightly more complicated than Nail state, but it's still an example of a product state in the sense that the ground state is written as a product of these dimers. Within each dimer, it's not a product state, but nevertheless, if you think of this as a unit, you can write down your ground state wave function as a product of these dimers. Okay. So these are possible ground state, but condensed matter physicists are interested in even more exotic possible ground state, which may be looking like this. Okay, so this is a linear superposition of the valence bond solid state, which is somewhat similar to the superposition we have seen in the EPR pair. It's a kind of gigantic version of an EPR pair where we have many terms in this superposition, and each term is given by a valence bond solid with different pattern of dimer covering. Okay. So this kind of state was envisioned by Anderson when he tried to understand the physics of high temperature superconductor, for example. Compared to previous examples, this Nail state or valence bond state, this state is more complicated in the sense that we may not have a well-defined order parameter to characterize this state. For the Nail states, there's the well-defined magnetization. We actually call it staggered magnetization because spins direction pointed by spins are kind of staggered between A and B sublattices. But we can define some sort of classical order parameter to characterize this Nail state, whereas states which may be looking like this, it may not be characterized by some sort of symmetry breaking or order parameter. We call this type of state a quantum spin liquid. Liquid here simply means the absence of spontaneous symmetry breaking. So this quantum spin liquid, since condensed matter physicists are still actively discussing the properties of putative quantum spin liquid state. We don't have a final theory for the quantum spin liquid yet, but this type of state may be possible. In fact, if we have So here, just for the example, I took a simple lattice, such as a square lattice. But this type of state may be realized if we have a geometrically frustrated lattice, as realized in this material, which has a themyscide, which has this complicated lattice structure called kagome lattice structure. Okay, so we don't know the ground state of this type of magnet, but it may be example of quantum spin liquid. Okay, but here one of the central questions is, if such quantum spin liquid state is realized, how do we know? How do we know the spin liquid is a ground state? So that is the one of the central question in modern condensed matter physics. So like I said, near state, for example, we know how to characterize them. If we just measure magnetization, that's or more technical term is a susceptibility or something like that. We can detect near ground state, but quantum spin liquid, how do we characterize a quantum spin liquid? Okay. Once again, we don't have a final answer for this question yet, but one genius idea, one idea is in fact to use quantum entanglement, or more precisely the entanglement entropy. So idea is to consider a part of, so we basically split the total system into two regions, region A and region B. Okay. So then we have a ground state of this type of system, and we want to know something about this ground state. So what we would do is to consider, once again, the partial trace of part of the system. So let's say we take a partial trace over degrees of freedom living in this region. So we are left with degrees of freedom living in this region A. So let's call it reduced density matrix rho sub A. Okay, so then we can once again talk about entanglement entropy associated to this reduced density matrix. Okay. What was discussed by Kitaev and Praskil, and also Levin and Wen, is to look at the scaling of this quantity as a function of the size of region A. Let's say region A has characteristic length L. So then, for a spin liquid which is gapped, which has a finite gap to excitations, this quantity behaves as a some constant times L. But there is also the term which is independent of this size L, which is usually written as gamma. Okay. So what was found out was that this gamma, which is known as the topological entanglement entropy, this is a universal number, as it turns out. So it's like a critical exponent which characterizes various kind of phase transitions. But this number, in this case, it characterizes the different kinds of quantum spin liquid. For example, for the most typical case, we get something like a log 2. It has a universal number. And if you detect this number, we can basically say we find quantum spin liquid. Okay, so yeah, so this is what I'm talking about. So we compute this quantity, for example, this model, which is the once again, it's a little bit distorted, but this is a Heisenberg. This is actually a variant of Heisenberg model on this Kagome lattice, and then we just do exactly what I just said. So we look at the scaling of entanglement entropy as a function of this subsystem size, and then we look at this extrapolate to here, and this is log 2. So this is considered to be a kind of evidence for the existence of quantum spin liquid. Okay, so the nature of the ground state of the Kagome-Heisenberg model is somewhat complicated, but this is a way to detect topological kind of spin liquid, particular kind of spin liquid. Okay?
Understanding why is negative.
Yes, it is very important to have a negative number here. In fact, that's kind of suggests that there's some sort of constraint. So that means it's a very strongly correlated system. Yes. Okay. It's like a gauge theory, so that's why we get the something contribution which is negative because of the constraint. Yeah, strongly coupled. Another question?
Yeah, since you start from the pure state and you trace off this, suppose now if I really just take this idea and around a black hole, does it really break the usual, the entropy is proportional to area with some non-trivial corrections to quantum gravity?
That's right. So usually we talk about only this part.
Yeah.
So this part is the area row term.
Yes.
This part is sub-reading. It may be for black hole, I don't know, because black hole we say it's a no hair, because there should not be properties other than mass, and angular momentum, charge, and so on and so forth. I don't know what this means in the black hole physics, but this is entanglement entropy. So, yeah, question.
You have this situation in spin liquid. That means you have a gap, right?
Yes.
The gap system.
Right.
How about if you don't have a gap, like we know that Fermi liquids in 2 dimensions they have a logarithmic correction
That's
for
right.
error law, and we also know some of this Dirac cone will give you some effect here.
That's right.
So what is in that case if you have Dirac cone?
So for the case of Dirac cone, we get something like center charge, which is another universal number characterizing the particular kind of relativistic gapless theory. That's again universal number. That can be used for the Fermi liquid. Once again, I think it's a coefficient of the logarithmic term is also related to Fermi volume and the size of this region A. So once again, it carries some universal information. Yeah, this is one example where we can use this entanglement entropy to detect states which we cannot detect by using the order parameter idea.
This is not, you cannot measure it in experiment.
Yeah, so now question arises, can we measure it experimentally? But that's a great question in fact, so because we are developing a lot of insights from the theoretical side, and if this question, can we measure entanglement entropy experimentally? If this question was asked, let's say 5 years ago, I had to say no, and they had to be a little bit apologetic. But now, because of the recent developments, measuring entanglement is still difficult, but it's becoming accessible. So I present 2 examples, and their experiments was managed to measure this Renyi entropy, which is basically like entanglement entropy, which I presented before. And then they also looked at the time evolution of this quantity after this something we may call quantum quench. So we start from some initial state, but then we let this state evolve in time. But then once again, we make this type of bipartitioning in space, and then we can measure entanglement entropy as a function of time. For example, this is an experiment from the Harvard group where they consider cold atomic system, which may be described by something like bosonic version of the Harvard model, Bose-Harvard model. Then they prepare basically two identical copies of such systems, and then they make an interference effect to measure quantum entanglement, this Renyi entropy. And then they see, let's just focus on this part. They measured entanglement entropy as a function of time, and here they actually put some sort of imperfection or randomness or disorder. So in such system, there is the prediction from the theory where entanglement grows logarithmically in time, and this is the log-log plot. So experiment sort of confirms the very slow evolution, slow growth of entanglement entropy in the log scale. This is another slightly more recent measurement of entanglement entropy using different technique. This is from the Peter Zora's group. They kind of came up with the protocol using randomized measurement. So they make a sequence of measurement. Sequence of random unitaries, and then they make a measurement. But then they figured out by looking at the correlation between the measurement outcomes, they can get the entanglement entropy. And once again, this is a Renyi entanglement entropy as a function of time. And once again, they confirm the very slow growth of the entanglement entropy. So, so once again, entanglement entropy is useful in the sense that we can access non-trivial properties of very complicated quantum states realized in quantum many-body systems, which may not be accessed by conventional probes like a susceptibility or the parameters, something like that. And it is also becoming possible to access such entanglement-related quantities in experiments.
Question. So we know that entanglement entropy here is kind of zero the Renyi entropy. That means if you want to know all these entanglement spectra, for example, for each lambda, you actually need Renyi entropy to infinite order.
That's
so
right.
You need everything.
That's
but
right.
here we have only second order Renyi entropy. I'm wondering what kind of information you really have. Is that enough for entanglement? Because we know that Renyi entropy is actually not a real entropy, which it cannot satisfy all these entropy properties.
Right.
So then Renyi entropy is certainly not really, to a second order, is not really enough.
So ideally, we want to get all moments of the radius density matrix. And here, experimentally, second moment is accessible. Higher moment is perhaps difficult. But we can also ask what kind of information can be captured by second. Perhaps not all not all properties, but some quantities.
Topological information.
Yeah. So topological entanglement entropy is known not to depend on the Renyi index. So second Renyi is actually enough to get topological information. Yeah. So, but I think there are other properties which we cannot get from the second Renyi entropy. Yeah. It's basically because of the technical difficulties.
I think area law is maybe not really from the Renyi. I don't know.
I think distribution of the radius density matrix eigenvalues tells you a lot more. Like in gapless systems, like area law, gapless system. For gapless system, there's a chance that only few Renyis maybe. Okay. Maybe one thing I didn't mention was that it's also closely related to the computational difficulties. So when you try to simulate quantum many-body system by using classical computers, entanglement entropy sort of gives you some sort of estimate how difficult it is to simulate a given system. That is also a big part of condensed matter physics. Okay. So today I want to talk about particular kind of many-body systems. So far I'm kind of speaking very generally a quantum many-body systems and quantum entanglement. But there are certain kind of many-body quantum system which are interesting on its own. For example, for high energy physics, or maybe even for condensed matter physics as well. So they are known as holographic systems, and there's various people contributed, but in particular Maldacena in '97 made a very specific claim for specific holographic quantum systems known as ADS-CFT as a first concrete example of this holographic duality. So in this story, we have we start from some space-time d plus two-dimensional, let's say d plus two-dimensional space-time, which is hyperbolic. It's a space-time. It's a Lorentzian system, but let's say it's some sort of hyperbolic space-time. It's a constant negative curvature. Here I just draw a constant time space-time. This particular pattern or texture represents it's a hyperbolic space. Okay. So Lorentzian version is known as anti-de Sitter space. Okay. So this is where this holographic duality takes place. And this system has a boundary. Okay. This system has a boundary. And on this boundary, we basically realize the quantum many-body system of our interest, or maybe quantum field theory of our interest. So that's a d plus one-dimensional system. Okay. Whereas a total system is a d plus two dimensions. So it's from the point of view of this many-body system in d plus one dimension, we are talking about a system with one more dimension. Okay. So there's another important fact. So in these holographic systems, let's say on the boundary we realize quantum many-body system or quantum field theory. In this d plus two-dimensional bulk, what we have is the gravitational theory. So this is a dictionary between quantum field theory, which does not involve a gravitational force, whereas in the bulk we have a gravitational theory living there. Okay. So that's why we call it a holographic system. We realize d plus two-dimensional gravity theory, which we can represent simply as a d plus one dimension different system, which lives in one less dimension from the point of view of gravitational theory. So that's why we call it holographic duality, relating two different systems living in two different dimensions. Okay. From this boundary quantum many-body system point of view, one could ask, why do we really need one more dimension to describe this system? Okay. And as it turns out, this one extra direction or one extra dimension is associated to the energy scale of this theory living in the boundary. So this was first discovered in particular quantum field theory, which has a lot of symmetry. So that is n equal 4 super Yang-Mills theory in 4 dimensions. And then this model can be solved by taking the n large, the SUN Yang-Mills theory with n large. And then it turns out that it matches, it is described by the gravitational theory, but living in one higher dimensions. Okay. So there's other various examples of holographic duality which has been discussed. But from my point of view, these holographic systems are interesting toy examples which we can use to study various non-trivial properties of strongly interacting many-body quantum systems. For example, my colleague at UChicago, Dan Son and companies, they studied the properties of quark-gluon plasma using this holographic duality, and they made a prediction on the viscosity of quark-gluon plasma. So the reason why I could not show that slide is that I have a nice picture of the quark-gluon plasma, which is perhaps has too high resolution. But this was, but they made a prediction on the viscosity to entropy density, entropy ratio, which is given by universal number 1/4π. And this prediction was tested by heavy ion collision experiment in DIC, and they basically confirm not exactly 1/4π, but it's something very, so the value which is very close to the value computed from this holographic duality. Okay. On the condensed matter physics side, a holographic quantum system has been used to discuss systems which goes beyond quasi-particle pictures. Okay. So another reason the next slide didn't show up is that I have a nice picture of high temperature superconductivity. So that's why this I could not show that picture. But the in condensed matter systems, there are many interesting examples where we cannot use quasi-particle picture. The example or situation where we can use quasi-particle picture is something like a Fermi liquid, where we have basically weakly interacting free particles, which we can use to describe the system. But certainly something like high temperature superconductors, we cannot use such a quasi-particle picture. So quasi-particle picture breaks down in strongly correlated system. But then what kind of progress can we make? So people propose to use holographic systems to learn something about systems without quasi-particle descriptions. Okay. In more recent years, people discuss a even more concrete model, which is called Sashedev-Ye-Kitaev model, which is a model of which is a system in 0 dimensions. So no space dimensions, but they are just strongly interacting 0-dimensional system, which was considered by condensed matter physicists Ye and Sashedev in 90s, but recently it was discovered that it is actually admits these holographic descriptions as found by Kitaev and other people. So now question is, for holographic quantum systems, how do we, what is the entanglement entropy? What is the behavior of the entanglement entropy in holographic quantum systems? So that was my interest when I was working with Tadashi. He's here, he's my collaborator. So we came up with basically the formula for the entanglement entropy in holographic quantum systems. So remember, I picturized the holographic system in this way. So I have a bog, which is described by this red region. That's the a hyperbolic space-time with some gravity living there. And they have a boundary. So boundary, this blue curve is represent my space or space-time for my quantum many-body system. Okay, and then like in this picture, I'm interested in the sub-region, let's say A, and then I'm interested in the entanglement entropy associated to this region. The formula we came up with is this formula written here. So basically we first look for surface in the bog which has two properties. Property one, it has to anchor at the boundary exactly the boundary of this region A. Okay, so it has to be anchored here and here in this example. And property 2, this surface, it should have a minimal surface area with respect to gravitational action in the bulk. And then we compute, once we find such a surface, gamma A, we look for, so then we compute the area of this minimal area surface gamma sub A, and then we somehow normalize by Newton constant for Gn. And then this is the entanglement entropy of the system. We tested this formula for various systems, and then we eventually got convinced that this gives you a correct entanglement entropy for holographic systems. And later, Lukowitz and Maldacena kind of gave us a sort of proof for this formula. What is nice about this formula is that in strongly coupled quantum many-body systems, calculating entanglement entropy is usually very, very difficult problem. It's a useful quantity, but it's a very difficult quantity to compute. So one could think something like for holographic systems, since it's a strongly interacting system, it may be very difficult to calculate entanglement entropy. But with this formula, it's very easy. It's just we just compute entanglement entropy using geometry. Okay. So this is the formula we found back in 2000. More recently, let me actually first summarize quickly. Yeah, so short summary is that basically there's a class of systems, holographic quantum systems, which are the systems which are described by gravitational systems in one higher dimensions. So they are good, interesting toy models to study properties of strongly coupled systems. And in such systems, entanglement entropy has a gravitational or purely geometrical descriptions in terms of minimal surface areas. In more recent years, people are interested in the reversing the logic. So here, idea is to learn something about many-body quantum systems by using their holographic descriptions. But many people are actually interested in the holographic duality themselves, because it's a very bizarre phenomena. Or in fact, many people are also interested in learning something about gravity, or even quantum gravity. So they basically reverse the logic. So then maybe by studying entanglement entropy in strongly coupled system or holographic quantum systems, maybe we may be able to gain some insight into space-time or maybe quantum gravity. That's the kind of very popular research topic. So let me give you one example. So along this line, people came up with a kind of discrete model of holographic systems. So here, this is the something we call tensor networks. So we have tensors represented by these boxes, okay, and these boxes are connected by these links, where tensors are contracted. Okay, this is one way to visualize some sort of many-body quantum systems. And the idea is that there may be some sort of tensor network of this type, which may mimic the properties of holographic quantum systems. So this has been done by these people. And what is interesting here is that this tensor network model, it is the tensor network which act as quantum error corrections. So I mentioned something about quantum computer in the very beginning, but in quantum computers, we have to protect quantum computers from errors. because the gate implemented by qubits, implemented by some physical device such as superconducting qubit, we may not be able to perform perfect quantum gates because there's some errors. Then error may propagate. Then we may not be able to perform useful quantum computations. That's something people worried about in the early days, but then people come up with the quantum error correcting scheme. So whenever some error occurs, we may be able to correct it if we're clever enough to set up the quantum computers. As it turns out, this tensor network model or discrete model of holographic quantum system act as a quantum error correcting code, and this gives you some sort of insight into the mechanism of holographic quantum systems. So far, people have used this quantum error correcting code to basically reproduce unknown properties of holographic quantum systems, including the holographic formula for the entanglement entropy. Okay, I will be using this later, so that's why I show this. Okay, so once again, quick summary. So this is about holographic quantum systems. It's an interesting quantum many-body systems where, so I think in part one, I emphasized the importance of the pattern or structure of quantum entanglement to understand quantum many-body physics. Holographic systems are kind of particularly interesting from that perspective because structure of the entanglement is somehow purely geometrical, right? Understanding structure of the quantum entanglement may be horrendous task in general, but holographic systems provide simple and interesting toy models for such kind of paradigm. Okay.
So you mean on the surface it's quantum field theory, right? Should be conformal field theory like Kepler system, or it could be everything?
Yeah. So the original example, you have a conformal field theory on the boundary. You could also get a gapped system on the boundary.
You also get gap system.
You can also get a gapped system. People also thought about maybe getting Fermi surface. People could not get Fermi liquid, but people may be interested in getting non-Fermi liquid on the boundary, or other systems. I think for this tensor network model, this I think they may have conformal field theory on the boundary.
So my question is, if I have, for example, the 1D Hubble models, for example, with some complicated interactive form, so I still can use your method to calculate the entanglement of that without any difficulty, because I haven't seen such calculation.
Yeah, so if it is a Hubbard model at critical points, then this computation applies. It's conformal field theory. But Hubbard model can realize various other kinds of phases, CDW phase, SDW, or some gapped phase, or maybe even.
So you mean if this is gapless phase, it's easier to tackle using this method. For example, I have a bilinear Barber model.
Yes.
And I have an SU3 phase.
That's right.
And that phase can be.
That phase can be described by this method. Yes.
But the Holden phase.
Holden phase is gapped. So then we have to realize first of all the holographic model which realizes the gapped boundary.
Yeah.
But then Holden phase has also topological order. So then we have to also ask how do we realize such order.
So still not realized, or
Holden model, I don't know. There's a proposal of realizing quantum Hall systems on the boundary. That has been done. Holden phase, I cannot think of any concrete proposal.
Thank you very much.
The last part I want to give talk about something more recent topic. So it's a holographic description of something called entanglement negativity. The question is basically the quantum entanglement in mixed quantum state. So when I'm discussing entanglement entropy, I start from a pure state, in this case the ground state of a given Hamiltonian. Then I consider radius density matrix. But I could think of as a starting point, I could think of having mixed state. In that case, as it turns out, entanglement, von Neumann entanglement entropy is not a very good measure of quantum entanglement, because it may also include a classical correlation, which has nothing to do with quantum mechanics. But then I think diagnosing entanglement in general mixed state is still a difficult problem. But there's one particular quantity, the entanglement negativity, which sort of works okay to diagnose quantum entanglement in mixed state.
But there are some states that can be not detected by it.
That's right. So that's a concept of bound entanglement and so on and so forth. So for example, the entanglement negativity which I'm going to present, it may not be the complete characterization of the mixed state entanglement, but it does capture some aspect. So what is it? So it uses the concept of partial transpose. So remember, for the case of entanglement entropy, we take a partial trace. So we basically decide not to look at this region D. Partial transpose is somewhat similar to partial trace, but in this case we take a transpose only for a subpart of the total Hilbert space. So if you have a operator n written in some basis of the Hilbert space, tensor product Hilbert space HA and HB, if you look at this equation very carefully, we take a transpose only for the second entries, but we are not touching the first entry EI and EK, whereas EJ and EL, they are transpose. So we are taking a transpose only for the Hilbert space B, but not for Hilbert space A. So this is a partial transpose, and how this can be useful. So to kind of demonstrate the usefulness of the partial transpose, once again I want to take the simplest example, which is this EPR pair. Okay, I start from this, so 0, 1, spin up, down. And then I consider density matrix. So this example is pure. In this example, I start from the pure state because that's easy for presentations. So then we will see what happens if I take a partial transpose. So as I prescribed, I now take the partial transpose for the second spin. So that's I swap here and here, and for first two terms, nothing really happens. But for the last two terms, if I exchange 1 and 0 here and 0 and 1 here, I get these terms. So I change basically my density matrix from here to the new density matrix, partially transposed density matrix. What we would do now is to look at the spectrum of this partially transposed density matrix. So this density matrix, since it's a pure state, eigenvalue should be 1 and then 0, 0, 0. 1 and 0, 0, 0. Yeah. Now, after taking partial transpose, eigenvalues are different, and now it is given by 3 1/2 and 1 minus 1/2. So that's very strange, because for density matrix, eigenvalues must be positive definite, like a Boltzmann weight or something like that. But here, well, we get a positive eigenvalues, but we also get the negative eigenvalues. Okay. So the idea is that this existence of negative eigenvalue, this may be telling us something about the entanglement which is included in the original state. Because if the state is simple classical state of this kind, then there's no off-diagonal term. So the taking transpose does nothing to this state. So in this case, density matrix stay invariant under partial transpose, and therefore spectrum also stays invariant. But in this case, in this example, spectrum is badly affected by taking partial transpose. So maybe how badly affected by partial transpose may be used as a diagnosis of quantum correlation or quantum entanglement in this state. That can apply to even mixed state. So that is called a concept of positive partial transpose criterion. So if you get the negative eigenvalues after taking partial transpose, it suggests some sort of quantum correlation. Based on this idea, we can also define a nice quantity, entanglement negativity, where we basically just count the number of negative eigenvalues after taking partial transpose, and I weight these eigenvalues by the magnitude of these eigenvalues. So this is called entanglement negativity. Sometimes it is also convenient to consider log of 2 times n to plus 1. But this is called logarithmic negativity. So I will be basically talking about this logarithmic negativity. So this quantity turns out to be a proper quantum entanglement measure in the sense that, in the following sense. So the entanglement entropy is a good entanglement measure for pure quantum state, because whatever operation you make, this entanglement entropy always decreases. That's basically the quantum entanglement is something you cannot create by regular unitary operations if you consider spin A and spin B separately. If you consider total unitary operation for the combined system A and B, you can create any quantum state. But if you limit your quantum operation only for spin A and only for spin B, you cannot create quantum entanglement. So that's basically can be considered as a definition of quantum entanglement. Quantum entanglement is something you cannot create by using local unitary operations acting for A and B. Okay? But as it turns out, for the mixed state, this property does not apply to entanglement entropy. So this is called monotonicity and local operation and classical communication. Entanglement negativity turns out to be a monotone under LOCC. So whatever operation you do for system A and system B, entanglement negativity always decreases. Okay? So that's basically a nice property of entanglement entropy. So it is qualified as being called a quantum entanglement measure. Okay, so this has been used to study various systems, including multipartite entanglement, or more recently, it has been applied to quantum many-body systems, quantum spin chain, or correlated quantum system. But now, since I presented the holographic quantum systems, a natural question arises, which is what is entanglement negativity in holographic quantum systems? Given the entanglement entropy has a nice geometric description in holographic quantum systems, we could expect that entanglement negativity also has a very nice geometric interpretation. That's something we have been working on for a few years by now. So here's a basic claim which we came up. So entanglement negativity on the boundary field theory of holographic system is given by this object in the bulk, some geometric object in the bulk, which is called the cross-section of entanglement wedge. Okay, so this is our recent claim. So let me step back a little bit, and then first let me tell you what is the entanglement wedge. Okay, so to describe the concept of entanglement wedge, I consider once again, I consider holographic system, but I consider entanglement entropy for these regions, region A and region B, and there's also the region which does not include it in these two regions. Okay, so if I'm interested in, for example, entanglement entropy associated to these regions, following the holographic formula, I draw just minimal surface areas. Okay, and this green curve, the area of this green region basically gives you the entanglement entropy for the combined region A union B. Depending on the size of these regions, minimal surface area can be looking like this, or if these regions is too big, minimal surface area may be given by this. So there's some sort of transition as you change the size of these two regions. So by computing entanglement entropy associated to these two regions, we can consider something of mutual information, which is given by this quantity, entanglement entropy for region A plus entanglement entropy for region B minus entanglement entropy for region A union B. Okay, so this quantity basically bounds any correlation or correlation functions between these two regions. Entanglement wedge is basically the region inside here, so that is bounded by. So yeah, let's not take the right picture, which is more interesting. So it is basically a region bounded by these two boundary region and minimal surface area. Basically, this green shaded region is called entanglement wedge. So this region is considered to be the region which represents the reduced density matrix for region A and region B. So this is entanglement wedge. So by cross section, I'm interested in some surface which basically cut this entanglement wedge into two regions, and one corresponds to region A and the other corresponds to region B. And I will be looking for the cross section which is minimal. In this case, it may be looking like this. Okay. So now coming back to this claim. This entanglement negativity is related to the area of this dotted surface. That is our main claim. So we were not the first who were interested in the quantum information theoretic meaning of this cross section, and there are other proposal or other kind of thinking, which is written here. So other people also thought about quantum information theoretic meaning of this cross-sectional area of entanglement wedge. What we found out basically is that this is actually given by the entanglement negativity. So to establish our claim, the first thing we did was to take the tensor network model of holographic duality, which I presented before, and just compute entanglement negativity within the tensor network model, or quantum error correcting model of holography. So we just go ahead and just compute it, okay? And here is just a quantum circuit representation, which I don't think I have the time to describe, but there's some quantum circuit, basically. It's just quantum circuit. If you just forget about holography, it's just a finite quantum unitary, finite depth quantum unitary circuit, so you just go ahead and compute quantum entanglement. That's what I asked to my graduate student to do it, and he did it. And then what he found is what is rather indicative. So this is the first kind of indication why we thought it is related to the entanglement wedge cross section. So if you compute entanglement negativity in this quantum error correcting code, you will get two contributions, which is given by here and here. But I think it is easier to describe in picture. So these two contributions is this red region. And this bulk region is corresponding to this. So I first describe entanglement entropy. It also has the two contributions: S, which is this red region, and this S rho B, which is associated with this black region. So in this example, I'm creating a hole inside this tensor network to mimic the physics of black hole. Okay? So for the entanglement entropy, there are two contributions. Basically, this red part is the quantum part, but this part just comes from the fact that we have a black hole. So we just heat up the system. That's why we make a black hole. But then reduced density matrix has two contributions. One from the quantum correlation, and the other just coming from the thermal contribution. Okay. But now if you consider entanglement negativity, we still have two contributions, but instead of having the entropy associated to this black region, it is simply replaced by negativity. But negativity for thermal distribution is simply 0. So basically we just lose this part. So we are just left with this red part for the entanglement negativity. So in this example, which is different from this previous picture, but this is in fact nothing but the entanglement wedge for the case where we have a black hole. Okay, so this is the first computation we did, and it indeed indicates that it is related, negativity is related to entanglement wedge cross-section. Okay, and encouraged by this, or inspired by this quantum error correcting code calculation, we now made a conjecture. Okay, so the entanglement entropy for full-fledged holography, like n equal for super Young Mills, or we will actually consider field theory in 2 dimensions. So I will just focus on 2-dimensional field theory with 3-dimensional bulk example. But this is generic proposal. So entanglement entropy is proportional to the minimal cross-sectional area of the entanglement wedge up to some coefficient. Okay, so this is our conjecture, and this coefficient can be fixed by basically by considering various limits, which I don't talk about, but we basically know how to fix this coefficient. Okay, and for the case of a 3-dimensional bulk with 2-dimensional boundary, we fix this coefficient to be 3/2. So this is the conjecture for this particular case, 2-dimensional field theory with 3-dimensional bulk. Okay, so now let me just tell you, we tested this conjecture because we know how to compute this entanglement entropy on the quantum field theory, and we just compare that with the cross-sectional area of the entanglement wedge. Okay, we tested this conjecture, and this is the result. So this blue curve is the area of entanglement wedge, which we computed from just using 3-dimensional bulk system. And the yellow curve is the calculation from quantum field theory. That's rather non-trivial calculation. So I did some calculations, but my calculation was wrong. but my collaborator corrected it. And then after that, we see this perfect agreement with entanglement wedge, this blue curve, and the yellow curve. There's some transition which is related to how we draw this entanglement wedge as a function of this distance between region A and B. But basically, these two calculations agrees remarkably. Okay, so that's basically convinced me that this conjecture is really true. We also have a proof for this conjecture, but I think I don't have a time to talk about it. Okay, so summarizing, we talk about partial transpose to define entanglement negativity, and in particular entanglement entropy for holographic system. We found out that it is given by a geometrical object, which is the entanglement wedge, or cross-section, minimal cross-section of entanglement wedge. Okay, other thing I didn't have a time to talk about was that this partial transpose turns out to be useful also to study topological phases of matter, such as topological insulator or topological superconductor, where you can basically come up with the formula for topological invariant, which label different topological phases of matter. But I don't have a time to talk about this. Anyway, so partial transpose turns out to be very useful operation to study quantum many-body systems. And there's a holographic descriptions for the case of holographic quantum systems. With that, I think I'd like to conclude. So thank you for your attention.
Any questions?
So your conjecture has a Renyi version of the.
Yeah, that's right. So we have actually Renyi version.
Okay.
But it's slightly more difficult to compute. The reason is that even for entanglement entropy, Renyi version is slightly more difficult to compute. There's some sort of something we call back reaction effect, which exists, and then we have to take care of it. But we do have a formula.
Okay,
So you maybe.
It's easier to
Yeah, exactly. So that's right. So second Renyi negativity is easier to compute. So we have some prescription. Yes.
Any other questions?
Maybe simple. So the holographic principle can also apply to boundary safety without unitarity.
Without what?
Unitarity.
Without unitarity. Yeah. So there's a proposal which uses. There's some proposal for holographic duality of non-unitary series by Ian Colgan companies. But I don't know much about it.
So we're still very recent.
That's actually rather old. I think more than 10 years old.
So here you consider the negativity for a pure state.
That's right. So
Can you do a black hole? And then
black
check
hole.
this
Yeah,
out?
actually I didn't show you, but here, yeah. So the two comments. So we could do this for black hole case, and then once again we tested the conjecture, and our claim basically is correct. But here we started with pure state, but after tracing out these regions, we still get the mixed states for A and B. So that's how we get the mixed state. Yeah.
But also for thermal state.
Thermal state we can also do. Yeah, we can also do it. Yeah.
So is there any chance to get the entanglement spectrum?
Yeah. Yeah, that's an interesting question. Yeah, so once again, that's more difficult, but that involves computing, for example, all moments of Renyi's, and we have to take into account some back reaction.
But if you get some very important like entanglement spectrum, for example, for topological system, you get some important information of that, then
That's
it
right.
probably will be enough for describing topological system. Don't need all of that, right?
That's, I think, what we expect, but I think nobody tested that. I think spectrum for negativity has been studied only very recently, and people studied critical system, for example, and the one-dimensional gapped system, that the spectrum of partially transposed density matrix. But I don't know any result beyond that. So I think that's still an open question. Yeah.
Is there any generic property of negativity that you can solve from this simple picture geometric coding?
Sorry?
I mean, here for 3 dimension is perfect. You have,
Yes.
But for higher dimension, is there any simple property of negativity, like inequality or those?
Yes. So
That you can solve from this geometric coding.
that's right. So there are various properties satisfied by entanglement negativity. But unfortunately, I don't know. For example, for the entanglement entropy, there's something called strong subadditivity, which is so restrictive, so you can kind of make use of it in a very nice way. Like you get basically renormalization group properties and the other properties. negativity, I'm looking for such application or properties, but so far we haven't been able to identify nice properties. Yeah, that's an interesting question.
Any other questions? Maybe students have some questions? Okay, so if not, let's thanks Shinsei again.
Yeah, thank you very much.